Good evening. I'm Josh Freeman. I'm the chair-elect of the APS April Program Committee, and it's a pleasure to welcome this evening's public speaker, Professor Katherine Freese. Katie received her Bachelor of Physics from Princeton University and her PhD from the University of Chicago, where she was part of a cohort of brilliant graduate students that included the current chair and chair-elect of the April meeting. Come on. Thank you, thank you. And our chair is just coming. She went on to postdoctoral positions at Harvard, at the Kavli Institute for Theoretical Physics, and a presidential fellowship at UC Berkeley before joining the faculty at MIT. She then moved to the University of Michigan, where she became the George Uhlenbeck Professor of Physics. She subsequently became the director of Nordida, the Nordic Institute for Theoretical Physics in Stockholm, in 2014. And in 2019, she moved to the University of Texas, where she is the Jeff and Gail Kodolsky Endowed Chair in Physics. Katie's many awards include the APS Fellowship, a Simons Foundation Fellowship, an honorary doctorate from the University of Stockholm, the APS Lilienfeld Prize, the University of Chicago Alumni Professional Achievement Award, and election to the National Academy of Sciences. Katie is well known for her contributions to cosmology, including models and observational signatures of dark matter, from annual modulation of the WIMPs signal to dark stars, as well as models of primordial inflation and the current accelerating expansion of the universe. She's also well known as a gifted expositor of science, including numerous public lectures such as this, and her book, The Cosmic Cocktail. Tonight, she'll be telling us about the mystery of dark matter in the universe. So please welcome Professor Katie Freese.
So can you hear me? Yes. So Josh, you forgot to tell about the low-flying orbitals. That's a private joke between us. But so let's turn to today's subject, the mystery of the dark matter in the universe. Before I begin, I like to think about antiquity. People from the beginning of time, well, the beginning of humans, must have asked some of the same questions that we do. What is out there? Where do we come from? Where are we going? So the same kinds of questions that we, in a scientific sense, are trying to answer now. In those days, they had creation myths for the beginnings of the universe. The thing that's absolutely remarkable is that as of 100 years ago, with the work of Einstein's general relativity in 1915, we have our creation story, the hot Big Bang. But the difference is that the hot Big Bang is basically correct. It's incomplete, but it's basically correct. So if you think about the advances in human knowledge, wow, it's just amazing. And not only that, but in those past 100 years, in the 100 years between 1915 and, well, 110 years and now, the amount that we've learned about the universe is just mind-boggling. So I'm here to tell you a little bit about what we do know, and ironically, focus on a lot of what we don't know. Soon after Einstein wrote down his equations of general relativity, other people applied the theory that he had written down to the universe as a whole, and realized that there were several different solutions to the equations, and that the universe could be expanding, contracting, or static. Einstein preferred the idea of a static universe, because that would have meant additional symmetry, that everything looked the same at all time, on the average. But in 1929, not much later, Edwin Hubble made some really important discoveries. He was working at the Mount Wilson Observatory, which is above Pasadena. In fact, when I had a sabbatical at Caltech, you look up there and you can see, at the top of the mountain, you can see the observatory and some radio towers or whatever at this point. And it was only until when I tried to bicycle up there that I realized that's really the same vertical drop as Aspen. So those observatories up there historically were very important. One of the things that Hubble was able to show is that there are galaxies besides our own. At the time of the great theoretical advances of Albert Einstein, astronomy still hadn't even progressed to the point where people realized that there's something beyond our galaxy. They thought all the bright objects we see are inside our galaxy. So Hubble proved that isn't true, and he also proved that the universe is expanding. So I'm going to try to briefly explain how that works. Basically, he looked at galaxies at different distances away from us and observed the atomic emissions from the stars in those galaxies. And what he saw was that the light, by the time it got to us, had been stretched. Here's an analogy on a balloon. Let's say you draw a wave on a balloon, and then you blow up the balloon. Well, that wave is going to stretch. So the same thing is true of these atomic emissions, because we know the wavelength of the emissions at the time they're emitted, but what he saw, those wavelengths had stretched. The universe is expanding. Einstein at that point was forced to abandon the idea of a static universe. In a very simplistic picture, on the average, galaxies are moving away from one another, and that's what we mean by saying the universe is expanding. Obviously, you and I are not moving apart. Our galaxy is a self-contained gravitational object that's not part of this expansion. This is kind of a nice analogy for the whole thing. So let's take some dough that will become raisin bread and put it in the oven. Here the raisins are analogs for the galaxies. As the dough rises in the oven, the raisins move apart from one another, not because they're doing anything, but simply because the underlying bread is expanding. And, well, this is, look, I've never made raisin bread, have you? But I believe it. But the difference between the raisin bread and our universe is that the raisin bread has a central point, but we don't think our universe does. We don't think there's any special point in the universe at all. That if we look at the universe from our point of view, or we move to another place in the universe, on the average, it looks the same. Now, I also wanted to talk about the idea of what is meant by a hot Big Bang. People usually interpret this as the idea that the universe started from a point, but that's not quite right. Instead, let's imagine that we look backwards in time, and in that case, everything is contracting, getting closer together, things are banging into each other. So this room would, of course, contract to a point. But what if the universe is infinite? Then no matter how much you contract it, it is still infinite. So in fact, once it gets really, really dense, it reaches the point where our laws of physics fail, and we have to combine quantum mechanics and gravity, and that's something we don't really know how to do yet. One of the approaches is string theory. People have different ideas how to do it. And so if you think about it, the Big Bang is really not a point in space, it's a point in time. And there's not really an explosion either, but if you want one, put one everywhere. Well, where do we stand in cosmology? As I was saying, the modern science of cosmology is about 100 years old. And what's amazing is how much we've learned even since the turn of the millennium. We now know the geometry of the universe. We know the total mass and energy content of the universe. We know the age of the universe. But there's so many fundamental questions that still remain, and one of the big ones that I'm going to talk about today is, what is the universe made of? As far as the geometry of the universe, when people applied the equations of Einstein to the universe as a whole, it turned out there were three possible geometries for the universe. It could be closed, and by the way, these are lower dimensional analogs, and so what this means is that you would be living on the surface of a sphere, or it could look like a saddle, or it could be a flat geometry. Flat simply meaning that ordinary laws of 8th grade geometry apply. So triangles look normal, angles add up to 180 degrees for a flat geometry, but on these other curved surfaces, the geometry is strange. So here these angles add up to more and here to less. That question, it's kind of amazing if you think about it. These guys, working in theoretical physics, it's always a guessing game. You feel like you're doing sci-fi. You don't know if what you're doing is right. So they were imagining, well, what if we make these assumptions about the universe? And they didn't know if it was correct, but the entire fundamental equations of cosmology are based on their work. They were right. And it took a long time to realize that. And we do not know now that the geometry of the universe is flat, and I wanted to say a little more about that. These are just fun pictures that show the three geometries. Here we have a flat geometry, WIMP, two parallel light beams never meet. Or if you have a saddle, then they diverge, or more fun, on the surface of a sphere, they come around and bite you from behind. The way we learned about the geometry of the universe is by looking at the leftover light from the Big Bang that was created about 400,000 years after the Big Bang. The universe today is 14 billion years old, so that was pretty early. And it's the size of, these are hot spots and cold spots of this light. They're all about the same temperature, but slightly hotter and slightly colder in different directions. And it's the size of these hot and cold spots that tell you about the geometry. In fact, if light moves in straight lines, we would expect a peak at 1 angular degree in scale, and look, whoop, there you go, 1 degree. So that's how we know that the geometry of the universe is flat. And I don't mean two-dimensional, I just mean there's no curvature. So if you take a cube, you stretch it in all different directions to infinity, that you have normal geometry, no curvature required. Before I leave this subject, I have to show in this the cosmic microwave background data, SH, Stephen Hawking initials. Okay, you saw it, there it is, SH. Okay. Well, that leads me to this question, the topic for today, what is the universe made of? And the answer is very surprising. If you take all the objects of our daily experience, your body, the air you're breathing, the chair you're sitting in, the cocktail that you'll be having later, the earth, the sun, all of that made of atoms. But all of that atomic matter only adds up to 5% of the universe. In fact, detailed studies of the cosmic microwave background and many other probes at this point show us that ordinary matter is 5%, dark matter is 25%, dark energy is 70%. Dark here simply meaning it doesn't give off light. And also, we don't know what it's made of. So that is what I want to talk about today. All right, so the picture of the Big Bang, it started 14 billion years ago in a hot primordial soup of particles, quarks, leptons, the fundamental objects inside atoms. And as time goes on, the idea of the Big Bang is the universe is cooling and expanding. Started out very hot and dense, but it's cooling off. This is my book on this subject. Here's a recipe that I'm going to talk to you about. The dark matter problem at this point is 90 years old. It dates back to Knut Lundmark in Sweden, and famously Fritz Zwicky, who was a Swiss scientist also working in the same telescopes I was talking about before. He was studying galaxies in a cluster called the Coma cluster. There's hundreds of galaxies in this thing. And he was watching the galaxies move around the center of the cluster, but it was hard to understand why their orbits around the center were so fast. Because based on the stellar light from the other galaxies, they shouldn't have been going that fast. They should have actually just been whizzing off into space if they're moving that fast, but instead there must have been some additional material, additional dark matter, or dunkle Materie in German, that was holding them in place. I do have to tell a story about this guy. In his book, he called his colleagues spherical bastards, because no matter what direction you're looking at them from, they're still bastards. Maybe not ideal PhD advisor. There was a lot of debate after that, but then let's fast forward to the 1970s to the work of Vera Rubin and Kent Ford, and they studied rotation curves that I'll show you and found that they proved that galaxies all have dark matter in there. So the scientific community was absolutely convinced the dark matter problem is everywhere. Let's do an analogy. This has nothing to do with dark matter, but it's a good analogy. It's the solar system. All right, so here I start at 0 is the sun, and as you move out, you get to the other planets. And this is how fast those planets are moving. So the closest planet, Mercury, is the fastest. And then we have Venus, Earth, Mars, da-da-da-da. They get slower as you move out. And instead of removing Pluto, I accidentally added planet 9, I guess. So ignore these guys out here. But I don't have a lot of equations in this talk, but I will put this one, which is telling you that the speeds of these objects, if you doubled the mass of the sun, if the mass of the sun were 4 times as big, then everything would be moving faster. So the mass that pulls on these objects tells you how fast they're moving. This kind of picture is called a rotation curve. And while I'm on the subject of the solar system, Tycho Brahe made a lot of these measurements. He lost his nose in a duel and wore a gold and silver replacement. He also, there was a big question about his death. So I'd always heard that he died at a dinner with the king because he had too much wine, and you're not allowed to get up till the king does, and his bladder burst. But I guess it was 20 years ago, there was a new theory, which is it was mercury poisoning by Johannes Kepler, his graduate student. Kepler's laws. Should they be Brahe's laws? Well, they dug up his body and they did all kinds of tests. Nope, no poisoning. I attest to the story about the burst bladder for the following reason. I was at one of these Nobel dinners. When the Nobel Prize is awarded to people, you invite some other people to the dinner. And so there I was in my ball gown, and I had to use the facilities. So I got up, I went to the bathroom, I came back and said hi to a couple people. There's the central table where the king and queen are with the Nobel laureates. By the way, the physicists get to sit right next to the king and queen. They're number 1. Anyway, so, and as I sat down again, I was reprimanded about if you're going to go to the bathroom, you should at least be very discreet about it. So I believe the story about the burst bladder. Uh-oh, I'm not going to get through half my talk, but that's okay. This is good, right? Okay, so let's get back to dark matter and talk about rotation curves in that context. It's exactly the same thing as the solar system in the sense that if I'm watching something move around the center of the galaxy, the speed it's moving with is determined by the mass interior to that orbit. So if there's more mass in there, then that speed is going to be faster as it goes around the center. Here's what Vera Rubin found. This is a typical picture of a rotation curve of galaxies. This is not from her work, but it's the same idea. Again, this time we're starting at the center of the galaxy and moving out as you move to the right. And up here, this is how fast things are moving around the center. And if it were like the solar system, this is what you'd expect. And based on stellar light, that's what was expected. But nope, these things are moving way too fast. So what you have to do is add in more mass, okay? And we add in a halo of dark matter, which I'll show in a second. Let's look at our Milky Way. All right, so our Milky Way at the center has a supermassive black hole, shown in yellow just so you can see it. And this led to a 2020 Nobel Prize in Physics for these two, for the discovery of that thing. It weighs about 4 million times as much as the sun. Now let's move away from that black hole. There are these spiral arms here, and you'll see the sun. It looks like a pinwheel, and here's the sun out here. This entire structure, these are the stars you see in the sky for the Milky Way. Well, let's turn it on the side, and that's called the disk of the galaxy. And here again, from the center of the galaxy, we go out 25,000 light years. There's the sun. But that is only a tiny piece of the total. Oh, I forgot to say, supermassive black holes are not the dark matter. Every galaxy has one, but they're only a tiny, tiny fraction of the universe as a whole. All right, so back on the Milky Way, there it is. This is obviously an artist's rendition. The spiral arms and the disk are right here. But look at this. That's where most of the mass is. And we call it a halo. Don't ask me why. of dark matter. It's a giant spherical object. Okay, so the first discovery of dark matter was through observing things moving too quickly. Something had to be pulling on them. Another way to look for it is Einstein's lensing. Einstein predicted that mass bends light. So if you have, that was, by the way, proven a couple years after he proposed it. So there's some dark matter here. I don't care what it is. This is massive compact halo object in this case, but whatever it is, the dark matter doesn't give off light, but what it does do is it bends the light that comes from behind it. So here's a star, but it gets bent. There's no kink, sorry, that's just my bad drawing. So so from the point of view of our telescope, you might think the star is over here. But then you'd notice, wait a minute, something's going on because I have multiple images of the same object. These are sheared images, they look funny. And based on the equations of gravitational lensing will then tell you what the mass had to be en route to explain what you see. In fact, there's an app on your iPhone that a University of Michigan student, Eli Rykhoff, put the correct equations in, and you can lens yourself. Okay, these are students lensing themselves more and more and more. Here's some actual data of lensed galaxies. This is a good one from Hubble Space Telescope. There's a lot of lensing going on in here with distant objects being lensed by stuff in front, and I don't even know all the details, but these are definitely sheared objects. These are definitely multiple images. Now, with a computer, you can reconstruct what mass it took to create those images. And if you do that, you get something like this. This is from different Hubble Space Telescope data, but it's just such a beautiful image. This tells you where the mass had to be to produce some of these lensed objects. And you can see there's a bunch of galaxies here. This is a cluster of galaxies. And there's also dark matter, a smooth portion of dark matter in between the galaxies. So clusters have additional dark matter, not just within, but also outside of the galaxies. All right, third piece of evidence for the dark matter, the bullet cluster. We happened to catch observations of two clusters that collided with each other. So they went through each other. And what happens when two objects like that hit? Well, the ordinary matter is shown in pink, so that's a hot gas. It gets stuck. It has electromagnetic interactions. It has strong interactions. It's as though you and I were to hit. We get stuck. So that's the behavior of the ordinary matter, but then there's something else. Oh, I like those question marks. I'm sorry about that. A different type of matter look at this, shown in blue, again, discovered by lensing. The dark matter behaves completely differently. It keeps going. It doesn't get stuck. It doesn't have those interactions. So this is, after the first collision, this is what you see called a bullet cluster because it looks like a bullet. Another piece of evidence for the dark matter, which I'm just going to whiz through, is this is interesting to think about. We as humans would not exist if it were not for dark matter because we needed dark matter to clump first in order to make galaxies. Then the ordinary matter could fall in. So starting very early on, if these are clumps of dark matter, there are simulations that show how that dark matter clumps, etc. And here's the universe today. Filaments of structure with the galaxies at the nodes or intersections of these filaments. Okay, so I've talked about some of the evidence for dark matter. There's a lot of it I have not talked about. There's also Big Bang nucleosynthesis, which showed atomic matter. This is 3 minutes after the Big Bang. You can prove that the amount of atomic matter cannot be everything. Then cosmic microwave background I mentioned. But still we have no observations of dark matter's non-gravitational interactions. We don't know what it is. All right, so back on this pie chart, we have to figure out what are the pieces of this pie. Immediately, people tried simple things like rocks or dust or snowballs of hydrogen and showed that they all don't work because they have observational consequences that don't happen. Okay, so what are the dark matter candidates that we would talk about today? Well, there are many. This is just some of them. I'm going to focus on these two because they're theoretically the best motivated, but first let me say something about neutrinos. Neutrinos exist. We study them very well, but I better not curse. Unfortunately, they don't solve the problem because they're too light, they ruin galaxy formation, and we now know how much they weigh. They're only 0.5% of the mass of the universe, so neutrinos don't work. But what, in addition to the active neutrinos we do know about, there's another proposition, which is sterile neutrinos. These are not the normal neutrinos, but they're very interesting candidates, and we have some adherents to this idea in this room. I'll let them speak up later. What's next on my list? Primordial black holes. I like to show people that have worked within my group. This is Florian Kuhnau. He's done a lot on primordial black holes. What are those? Well, they would have been born when the universe was very, very young, whenever you have severe overdensities. So in one region of the universe, you'd have so much stuff that it would implode to a black hole all by itself. These things can be smaller, typically, and they're very interesting candidates for the dark matter. Especially, there's been a resurgence of interest because in 2016, for the first time, the LIGO detector found something that Einstein had also predicted, gravitational waves. When I shake my hands, I'm making gravitational waves that are so tiny you can't see them, but merging black holes, aha. Now, that was what was discovered. And this is pretty cool. This is how the gravitational waves were detected. And those objects, some of those black holes they're finding could be primordial black holes, could be the dark matter. But back on my list, I mentioned that there were two in particular, axions and WIMPs, that I'm going to focus on because they're the theoretically best motivated. Why do I say that? Well, they have reasons to exist that have nothing to do with dark matter. They were proposed anyhow, independently, in work in particle theory. They solve some problems of particle theory all by themselves, and in addition, give you these nice dark matter candidates. I won't say much about axions. They're very light particles, but they're moving very slowly. They're very good dark matter candidates. And I did want to say they were simultaneously proposed by these two guys, Steven Weinberg and Frank Wilczek. And I have to have a few slides about Steve Weinberg. Perhaps, definitely one of the greatest minds of our time, one of the founders of the standard model of particle physics, explaining the quarks and leptons that make up our atoms, our atomic universe. And his office was 3 doors down from me. A major loss for us and for the world. We now, since he died, we now have a Weinberg Institute for Theoretical Physics. I'm the director. You forgot to say that, Josh. It's okay. I'm saying it myself. And we have 3 centers inside the Weinberg Institute: cosmology, gravitational physics, and particle theory. And we had an inaugural conference in November, and we're going to have many other interesting activities in honor of the great Steven Weinberg. All right, so this idea of axions it's a great idea, but then now what's happening now is a lot of experimental efforts to look for them. And this is, again, someone who used to be in my group, Luca Visinelli. And it shows you these are the mass of the particles and their interactions. This yellow curve would be the one that solves the problem in the strong interactions. That was the original motivation for the axion. But people are trying other variants now from string theory, other axions, and so on. So this is a very active field of research on the experimental side, and I'll leave it at that. Let me turn now to the other top candidate for dark matter particles, and that is WIMPs, weakly interacting massive particles. A reporter once asked me, so we wrote a paper on it, believe it or not. Billions pass through your body every second, and somewhere between 1 a day and 1 a month hit one of your nuclei, and you're still around. So that tells something about how weakly interacting these things are. That's why they're so hard to detect. They do not feel the strong forces. They do not feel electromagnetic forces. Yes, the definition of matter is they feel gravity. Now, of the 4 fundamental forces, there's one more remaining force, and that's the weak force, responsible for some types of radioactivity. And that's what we're going to postulate, that you've got particles that are weak, the WI, weakly interacting, and as far as mass, they weigh 1 to 10,000 times as much as protons. Okay, so, whoops, I've got much, don't worry about the equation here, but I'm just putting it there to make the point that one of the reasons that WIMPs are so great is the only postulate you have to make is that these particles were around in the early universe. They annihilate among themselves, they're special in that way, and if that annihilation is determined by the weak force, you end up with the right number of WIMPs around today to solve the dark matter problem. So that coincidence, some call it the WIMP miracle, is motivating people to take great interest. The other one is that these things are already around in particle theory such as supersymmetry. In supersymmetry, every particle we know has a partner, and the heavier ones decay to the lighter ones, and the lightest one would be stable. It could be the dark matter. Well, so they're theoretically motivated, but where are they? Well, there's the three-pronged approach, and I want to talk about my idea of dark stars also. I hope I have some time. So you can either you make them, shake them, or break them. Let's start with making them. This is the Large Hadron Collider at CERN in Geneva. Yes, you can ski up here. This is a 17-mile ring where protons are accelerated in opposing directions to nearly the speed of light and then smashed into each other at various detectors. Just showing some pictures of the people involved. One of the detectors, the spokesperson for some of the work there, and now Director General overall of the entire place. Oh wait, I think, did she just step down? Anyway, so she was for many years the director. And this is what the detector looks like. There's a human. Impressive technology. Peter Higgs, if you've heard about the Higgs boson, there he is in front of one of the other detectors. In fact, the last remaining piece of the standard model of particle physics was the search for the Higgs that weighs 125 times as much as a proton, and there it was, discovered by the LHC. The LHC, this collider, has also been searching for supersymmetry, searching for dark matter. The way it would work is two proton colliding would give rise to a chain of supersymmetric particles, with the lightest one escaping the detector. So you'd have missing energy. Unfortunately, no discovery yet. It's a disappointment, but, well, let's wait and see what happens. More data to come. And let me turn now to, so even if you saw that something, if you found them at that Large Hadron Collider, you still wouldn't know it was the dark matter. You'd know you discovered a new particle, but dark matter is supposed to last the age of the universe. Let's do something more direct. Let's instead, I told you there's a billion of these things going through you every second, so put a detector. Let the WIMP hit the detector. And that's exactly what happens in these direct detection experiments. The goal is that the particle would hit a nucleus, deposit a very tiny amount of energy, and then scatter off again. But really hard experiments. Very tiny amount of energy. I wanted to tell you how I got into cosmology and studies of dark matter, and the answer is my PhD advisor that Josh was pointing to the University of Chicago back in the day. David Schramm was one of the founders of this field of astroparticle physics, and as others here know, yeah, Jim, I'm looking at you, our nickname for him was Schrambo, because he was an Olympic hopeful, and he was a very big guy and loved a lot of sports. If you skied with him, where there was a mogul, after he went through it, it was gone. So he was fantastic, very inspiring, wonderful guy. Okay, so moving forward in my career, then I was a postdoc at the Harvard Center for Astrophysics, where I worked with these two guys, David Spergel and Andrei Drukier, and we did some of the earliest calculations of the scattering. I did the particle physics of the WIMP scattering off of nuclei. David did the astrophysics of how many there are in the galaxy and so on. And, well, what can we say about him? I'll tell you later. He speaks a lot of languages at the same time. Now, one of the things about these detectors is there are competing signals from cosmic rays. We are being bombarded all the time by particles that are dangerous because they have electromagnetic interactions. If you go up in altitude, you're going to encounter more of them. A big problem for astronauts. A problem for pregnant women flying over the North Pole because they're attracted by the magnetic field, i.e. flying to Europe. So in order to get away from that, you have to go deep underground. You have to go about a mile underground. And this is, for example, in the Gran Sasso Tunnel outside of Rome, the xenon experiment. When we did these calculations, we never thought this was going to happen. It's an underground experimental effort everywhere in the world. And, well, the trouble is no discovery. So there has been hope that one of these experiments, that was also in the same tunnel that I just showed you, this DAMA experiment. Where is it? There it is, DAMA. That what it's sensitive to is the annual modulation of the signal, because as the Earth goes around the sun, the count rate in detectors should be different. We predicted it, and their data match it absolutely perfectly. But why don't we claim this? Why they're claiming discovery? Why don't people believe it? Well, two reasons. They won't let anybody see their data, and other experiments don't confirm these results. So the comparison used to be, oh yes, this is also really fun. The people in these groups, these are PIs of some of these groups. As Juan Collier says about the PIs of Xenon and DAMA, I'm a Spaniard caught between two Italian women. And people, you know what they say about Juan? They say he's the straw that stirs the drink, whatever that means. Anyway, these are really fun people. They're all really good friends of mine. So, all right, so I was saying, well, let's see. These are different. How are we going to compare different experiments? They're made of different materials. That's a problem. If this is the mass of the particle, this is how strongly it interacts. All right, so the DAMA, if you want to explain DAMA, it would be these green regions. But these other, you have to be below these curves to be consistent with those. But what's going on here? These are different materials. You had to assume very specific details about the experiment, about the interaction. Spin independent, which may not be right, in order to put them all in the same plot. Yeah, this is out of date, but the story hasn't changed. Well, however, there's a new development, okay, which is that other groups are now using the same material. There's 4 different groups using the same material. And this cosine 100, but also on ice, not today. I was supposed to take that out. This was last summer, showed they disagree with DAMA in terms of dark matter interpretation, so looks like DAMA is on the way out. We're not sure yet. Okay, so what have we been doing since? We have new ideas for dark matter detection. I'm not going to talk about the DNA one very much. You can ask me about it later. Well, I'll just briefly mention strands of DNA hanging from, in this case, gold. WIMP hits the gold. Gold knocks out the DNA. That's one idea for a dark matter detector. But the one that's really happening is paleodetectors. Here the idea is, instead of using these experiments I was telling you about, like the xenon experiment, it's tons of xenon. It's really giant beasts. Instead of that, take a tiny little rock, but take it from deep underground, where it's been collecting tracks for 500 million years. So you're exchanging size for time. That's a much cheaper alternative. And these guys were in my group. And to my amazement, yeah, we wrote some papers saying you could look for dark matter, you could look for the history of supernova going off in our galaxy, you can study cosmic rays if you do it above ground, you can do all kinds of interesting stuff. Never did I imagine that they would, next thing you know, I'm going to a conference in Trieste in Italy, and they're who's there? People from Japan, from Germany, from Virginia Tech, and they're all actually excited about this, and that was a few years ago. And guess what? One of them, the Virginia Tech guy, is using color centers, and he got us all involved. There's a National Science Foundation $2.5 million grant to do this. And Josh Spitz at University of Michigan, which is where I used to be, $1.5 million grant to do this. So this is actually happening. So that's really exciting. And it's not just for dark matter, it's for a lot of other things. Also nuclear reactors, you can use them as tests. Obviously not the deep underground ones, but the same readout technology. So interesting new topic. Guess where I'm going next week? The UCLA Dark Matter meeting. Yes, and the Baja Cantina. Okay. The third way to search for these particles, I'm not going to go into a lot of detail, but in this case, remember I was telling you that in the early universe, these particles annihilate among themselves, and that's how we know how many are left? Well, we can also look for, in today's universe, the same annihilation. Wherever there's an overabundance of these particles, they're going to annihilate and give signals you can look for. Here's the kind of thing that happens. Two dark matter particles annihilate into a chain of other things. In the end, what you get is about a third neutrinos, a third high-energy particles of light called gamma rays, and a third positrons, which are the partners of electrons. So it's the same annihilation that took place in the early universe that gave you the right amount of dark matter. It's the same annihilation that I'm about to talk about for indirect detection experiments that look for these annihilation products. And in dark stars, we're also going to power stars using the same annihilation process. Well, I mentioned that the things that come out of the annihilation in the end would be neutrinos. So there's the ice cube detector at the South Pole. And several kilometers below the ice, you've got these strands of detectors, and there's the Eiffel Tower just for size comparison. Amazing technology that they're successfully studying high energy neutrinos. It's a very cool detector. Then aboard the International Space Station, they found excess positrons, but nobody thinks it's dark matter anymore. This is the one that has hint of signal. This is the Fermi Space Telescope, which is looking at the gamma ray sky, gamma rays being the highest energy photons or particles of light. And what they see, there's the gamma ray sky they see, and smack in the middle, these giant bubbles are fun. But smack in the middle there is an excess that nobody knows exactly what's going on. If you remove everything else, there is an excess gamma ray signal. Could that be from dark matter annihilation? A lot of discussion heading in plus and minus, is it, isn't it, pros and cons, but it still remains a very interesting signal. Oh, yes, I do have some time to talk about dark stars. I'm not behind, look at that. Okay, so this was our idea, and yeah, it's the same dark matter annihilation, and we're going to see that it can power the very first stars that form. Okay, as I said, this is, in addition to the third prong, there's this fourth way to look for dark matter. This was an idea that I had with Doug Spolyar and Paolo Condolo in 2007. And yes, we didn't know about this cult film at the time. We named it actually after a couple of songs, Grateful Dead and Crosby, Stills, Nash & Young. This is a terrible movie. I highly encourage you to watch it. It's pretty funny. Bombed out in space with a spaced out bomb. Okay. So, dark stars. We're talking about the first stars to form in the history of the universe. And that means 200 million years after the Big Bang. So please remember the universe now is 14 billion years old. So 200 million is still pretty early in that sense. And the idea is that these things would be, let me emphasize right away, dark stars are made of ordinary matter, okay? They're made almost entirely, 99.999% of hydrogen and helium from the Big Bang. That's what they're made of, hydrogen and helium. Tiny bit of dark matter, however, is enough to heat them up. It's their power source. And these very early stars have the dark matter annihilation in there, but no fusion, so they're weird. And this is kind of an outline of what happens. They can grow until they're very large, like 10 million times the mass of the sun, or 10 million times as bright as the sun. And there are two consequences of that. One of them that I will talk about is if they're that bright, well, then then we have candidates in the James Webb Space Telescope that I will tell you about. The other consequence is that once they die, they collapse to supermassive black holes, which is great, because there's a lot of them out there that people don't know how to explain. Okay, so the basic picture, I've said the first sentence is I've said before, these formed 200 million years after the Big Bang, and where are they? In the centers of protogalaxies, okay? So the way galaxies form is you start out with smaller mini halos, little galaxies. They merge together to make bigger ones and so on. And so that at this point there would be small ones around. And the thing that's really important is that you have smack in the middle of these mini halos. That's where this process happens. That's a very dark matter-rich environment. What happens is you have a cloud of hydrogen that begins to collapse en route to star formation. And as it does that, it pulls in even more dark matter gravitationally. Well, the dark matter starts annihilating because it's packed in so tightly. And the annihilation products, as I've been saying, include, well, E plus, E minus, the electrons, positrons, and gamma rays, photons. Those things collide with the hydrogen. They're trapped inside the cloud, and they heat it up. They don't escape. So most of the annihilation products don't get out. And eventually, the dark matter heating is so strong that it prevents that cloud from collapsing anymore. And in fact, it turns into a star, a dark star, powered by dark matter. Dark stars are very, very weird. They, in radius, they're about 10 AU. In other words, 10 times the distance between the Earth and the Sun. So these are really, they're really giant in terms of size. And they start out weighing about the same mass as the Sun, but then they can keep growing and growing and growing and growing. And why can they do that when other stars can't? They grow by accretion. There's mass around, and the mass just falls onto them. They can just keep accepting more and more mass. Why can they do that? Other stars can't? The reason is that they're very, very cool. Their surface temperatures are very, very low compared to other things. Don't forget, we don't have any fusion here. We don't have a hot core. There's nothing hot about this thing anywhere. Dark matter annihilation doesn't care about the temperature. So you've got dark matter annihilation spread out throughout this whole thing, and the surface is cool, so more mass can fall onto it. It's, I guess I've written it here, not blowing off hot material that prevents further accretion. All right, this is a picture of how we built up one of these things, and this is it's called a Hertzsprung-Russell diagram, but as you move to the left, you're getting hotter, and as you're moving up, you're getting brighter. So let's follow one of these curves. There's a bunch of different parameters in here, like different masses of the particles. Anyway, let's follow one of these, and yep, this thing just keeps growing and growing, and we cut it off, but it can just keep growing to be 1,000,000 times as massive as the Sun and 1,000,000,000 times as bright. So we did this on the computer, sequentially with more sophisticated codes, and we found this mass scaling with the scaling with the brightness, and guess what? We found that in a paper from 1952 or something by Fred Hoyle. So that the correspondence of mass and brightness was known all along, but what we provided was the heat source. Okay, so as I said, it's helped solve the big black hole problem. After the dark stars die, they collapse to 1,000,000 solar mass black holes. That's great, because those can merge together to make these guys. This is 10 billion times as massive as the Sun. You've got early black holes that the James Webb Space Telescope, is finding all over the place. How in God's name are you going to make them? You start with a seed, a supermassive black hole formed from collapse of dark stars. All right, observing dark stars with the James Webb Space Telescope, which launched, I guess it was 2 years ago now? 2 years and 3 months. And basically one supermassive dark star would be as bright as an entire galaxy of stars. So we proposed dark stars in 2007, and then in 2010, John Mather, the Nobel laureate who pushed for the existence of the James Webb Space Telescope, said, hey, tell us what to look for. So we made some predictions. So my grad student at the time, Cosmin Illy, has been really carrying this forward. And this is the work that he did back then. These are different. These lines here show you what you have to be above those lines for the James Webb to be able to see anything. Yep, our predictions were that you'd be above those lines. And here's the status of a year and a half ago. We looked at the James Webb, the JWST Advanced Deep Extragalactic Survey, or JADES, of the 4 objects from very early, from very far back in time. That we discovered that 2 of these, of the 4, 2 of these could be dark stars. We thought a third one could, but actually these 2 are candidates. This is a prediction for how much light would come out at different frequencies, and it works. So I'm going to just skip ahead and show you an example. Okay, so this is the brightness, and this is the wavelength or frequency of the light, and the black dots are the data, and this is one of our curves, so you can see that we're fitting this C spectra very well. And so I guess the bottom line here is that the James Webb Space Telescope has found many high redshift objects, okay? But that means they're very, very early in the history of the universe. Too many and too massive. It doesn't seem to fit the standard picture of cosmology. What is going on? There's a big debate. Are there too many? Are they too massive? Two separate problems, people arguing about this. Fine with me if that's true. The standard cosmology breaks based on this? It's just that they found that some of these are dark stars. And just as a reminder, one supermassive dark star can be as bright as an entire early galaxy of stars. Okay, so this particular slide has my excitement, and it's a bit too technical for today's talk, but I'm just going to say that, oh, by the way, dark stars need some heat source. It doesn't have to be WIMPs. Any kind of dark matter that deposits heat in the star will work. So we're investigating what other types of dark matter would do that. Well, I mentioned all these different ways of looking for dark matter, so we'll see what comes of it. I am going to end with a joke. Well, I have a minute and a half to talk about the dark energy that makes up 70% of the universe. There's only one thing we know. All of matter, dark matter, ordinary matter, it all feels gravity. It all feels gravitational attraction. It clumps together. Dark energy is, it's probably a misnomer, invented by, well, Josh is not listening, so I won't say. Anyway, so dark energy is something that's causing the expansion of the universe to accelerate. Not are the galaxies, they're not just moving apart, they're accelerating even faster. They're accelerating apart from one another. What is going on? Something repulsive is going on. We don't know what. Now, the same picture I had before, but imagine these galaxies accelerating apart from one another. We don't know on the theory side what's going on. We don't know on the experimental sides. There's interesting talks at this conference. But what I wanted to talk about is this panel that I sat on with these Glennis Ferrar is here, and Eleanor Prelay will be at the dark matter meeting. We talked about dark matter, and this is at the World Science Festival in New York. And these three guys were talking about dark energy. And there's only one thing we know, okay? Do I have to go back? Okay. Dark matter, dark energy. Okay, so there you go. And I'm just going to end with, this is my book, The Cosmic Cocktail, 3 Parts Dark Matter. I was told not to say this, but there was supposed to be a setup of books in the back of the room. They're here, so I'm allowed to announce it? Okay, in the back of the room. Okay, just outside the back of the room, there's going to be a table with, I will do book signings for this book. And here's the recipe. As I said, supermassive black holes are in here somewhere. I was reading really tiny. Where are they? Where are they? Where are they? Here we go. 1/1,000,000 of an ounce. This is a 10-ounce drink. The ordinary stuff, not much. Yeah, dark energy is big. And 3 ounces out of the 10. Okay, fine. 2.5 ounces dark matter, shaken, not stirred, in the very early universe. Okay, so I think I'll stop there.
Thanks, Katie, for that great talk. We do have time for some questions. So if you're interested in asking a question, please come up to one of the microphones and identify yourself and ask a short question. Everyone else, I'm sure you're streaming back to get to the books before they disappear, but after the Q&A, Katie will be outside in the back signing copies of the book. So why don't we go ahead on this side.
Hi, I'm Coronel from Ohio State University. You mentioned that the dark stars can grow up to 10 million solar masses. I assume that's for WIMP dark stars. What is the limiting factor there that limits it to 10 million solar masses?
So the original mini halos they form in are going to merge with other mini halos, and as long as you stay at the center, they can keep growing. We don't know what the cutoff is. Then that's really a cosmological question about what happens to the dark matter halos that they're sitting in. So answerable question, but simulations required. The other thing is that if the dark stars last long enough, then they would have been seen by the Hubble Space Telescope. So that gives you some kind of cutoff. But of course, if they form early enough, then for all I know, they get even bigger.
Thank you.
And on this side, over here. Go ahead.
Thank you. Thank you. My name is Wayne Costi. I'm an independent, interested person. With all the energy that is displayed in a gravitational wave, which collapses and rarefies space, it's an enormous amount of energy that has no residual impact, it seems. If that's how much energy it takes to expand space, the expansion of space as part of the cosmological expansion should be not just 90% or 75% of the total energy budget. It should be like 99.9999% because it's so much energy to stretch space.
The contribution of gravitational waves, energy-wise, to the entire universe is tiny. Does anybody know the number? 10 to the minus 16 or something, right? It's really tiny.
But it wasn't the question in the gravitational wave itself. It's that to me, it suggests that there's a huge amount of energy to stretch space. And the cosmic expansion that we all know about is space is expanding like under the dark end. It seems like there should be a huge amount of, really huge amount of energy.
I'm going to suggest we take this afterwards, after the Q&A. You can follow up. Next question over here on this side.
Hi, my name is Martin Johnson. I understand that neutrinos have been excluded as a possible candidate for dark matter.
Yeah, honestly, back in the 80s.
My understanding is that there are two substantive issues surrounding that. One of them is lepton number.
I can't hear you. What?
One of the substantive issues surrounding that exclusion is the concept of lepton number conservation, and the other is the fact that they're held to be too hot pretty much. They move too fast.
That was true initially, but you know what we've got now? Their masses. We know their masses. The sum of the masses adds up to about 0.1 eV. That's 0.5% of the content of the universe.
So can they be real cold? Can we allow for the possibility of really cold neutrinos?
I don't think so, but the numbers just don't add up anyhow, so.
Would that be lepton number conservation?
You know, my first paper was on how does neutrino lepton number violation affect galaxy formation. And so there's no big changes come about because of it.
Hey, one more on this side.
Hi, I'm Arnav from the University of Florida. I had a question. You'd mentioned that primordial black holes have been proposed as a potential source of dark matter. I was wondering, you talked about how like the dark matter distribution around.
Oh, I'm looking in the wrong direction. It's very bright here. Okay, sorry.
So you mentioned how the dark matter distribution around galaxies forms these halos. If, say, primordial black holes were a source of dark matter, how would they form in these halo kind of structures around galaxies? How would
they would have formed, they're called primordial because they would have formed very early in the history of the universe. For example, if there was a phase transition, like water boiling, but the opposite as the universe cools, then there can be wild fluctuations where there's a lot of mass that suddenly shows up in a small region. And that's the kind of thing that it takes for them to form. But it's very early in the history, in fractions of a second. of the age of the universe.
Okay, thank you.
So I'm afraid that's all the time we have for questions. If you do have further questions, Professor Freese will be around. Let's thank her again for a great talk.